This is the first and the last lecture which will cover all the topics related to Routh-Hurwitz criteria. There are two definitions for the stability of an LTI system. The first one is when a system is excited by bounded input, the output should also be bounded. This condition is also referred as bounded input bounded output condition. In other words, a system is stable if its impulse response approaches to zero as time approaches to infinity. The second definition is in the absence of input, the value of the output tends towards zero irrespective of initial conditions. This stability condition is known as asymptotic stability or zero input stability. We have also seen earlier that there are two types of stability. One is absolute stability and the other is relative stability. But the Routh-Hurwitz criteria is a method which is used to determine the absolute stability. In this lecture, we are not concerned about finding the relative stability of the system. We have to simply tell whether the provided system is stable or not. If you think carefully, then you will realize the stability is also dependent upon the input, but that point is also covered in the first definition of stability of LTI system. As you can see, we have to follow the bounded input, bounded output condition. But again, it is practically not possible to consider all such bounded input signals. Generally, if in some cases you have to verify your result for bounded input signals, then students usually take two types of input. One is unit step input and the other is impulse input. As these two signals are quite unique. One signal is having infinite duration but provides constant magnitude and the other is having infinite amplitude which lasts for only a very small time. In the second definition, we have seen that the definition of stability does not consider the initial conditions. But whatever we have studied so far, we have always considered systems with zero initial conditions, and that will apply in this lecture also. However, if there is a system with non-zero initial conditions, the procedure remains the same, only few steps increases. But for now, we will consider only those LTI systems which has zero initial conditions. Let us assume we are having a characteristic equation of nth order. Now, you have to form a table in which the first two rows can easily be filled with the elements by merely looking at the characteristic equation. As you can see clearly, in the first row, the coefficients of alternate terms of the characteristic equation are written and the remaining coefficients are written in the second row. Now, to form the further table, you have to do some simple calculations. For example, the value of v1 is equal to an minus 1 multiplied by the coefficient an minus 2 minus an multiplied by an minus 3, the whole term being divided by coefficient an minus 1. Same way we can find b2. Rather than remembering the formula of v1 and v2, it will be much better if you remember it through the table like the position of different elements which are present at different arrows which are making a cross. The next row also will be calculated in similar fashion and you have to keep on calculating different values of different elements in this table. This table is having different names like Routh table, Routh matrix as well as Routh array. The question still remains how we have to determine whether the system is stable or not. Now comes the Routh stability criteria, which states that the system is stable if and only if the elements of the first column of Routh array have the same sign. Otherwise, the number of roots of characteristic equation with positive real parts are equal to the number of sign changes in the first column of Routh array. Let us solve a problem through which you will definitely get clarity. I have taken a random transfer function. Now we will see whether this system is stable or not. Since the highest order of the S is 4 in this characteristic equation, there will be 5 rows in the Routh table. The first two rows can be formulated quite easily by simply looking in the characteristic equation. Now, we will try to find all the values of the elements which are present in the third row of the Routh array. The first element will be equal to 5 into 6 minus 4 into 7 divided by 5, which will come out to be equal to 0.4. The second element will be equal to 5 into 8 minus 4 into 0 divided by 5, which will eventually come out to be equal to 8. This 0 in this expression came because there is no element in the third column of the second row. So, we have also found the third row of the Routh table. In the same manner, we can also find the next two rows. Now, in the Routh table, As you can see, the first element in the third row is 0.4, whereas in the fourth row it is -93. We can see clearly one term is positive and the other term is negative. It means that there is a sign change, and since there is a sign change, we can say this system is unstable. In the question, we have to simply tell whether the system is stable or not. But what if the question is slightly different? For example, if we have to find the number of roots which lie in the right half of S-plane, then we have to calculate all the sign changes, which is 2 in this case, which simply refers to the fact that there will be 2 roots in the right half of S-plane. We can also say that there are 2 roots which lie in the left half of S-plane, as the total number of poles in this transfer function are 4. Now there are 2 points which will help you in calculations for finding different elements of the Routh array. The first point is all the elements of a row can be divided by a positive constant for simplifying the calculations, provided the positive constant which you have taken is a common factor of the elements. Now let us see the previous question once again. The root table we have already formed, but we are going to solve it once again. In the first row, we can see there is a common factor which is 2. We will divide all the elements in the first row by the term 2. Now, replacing all the elements in the first row, we will again solve the root table. You can try it by yourself. You will find that few values in the root table have changed. But again, if you are going to find whether the system is stable or not, the result will remain the same. In both the cases, there are 2 sign changes, which means that there are 2 roots on the right hand side of the S-plane, which determines the system is unstable. The second point is actually a point which students have to develop and observe through practice only. But still I am going to tell you. You can see the last elements of few rows are identical to the last elements of other rows. This happens because only the presence of 0. For example, consider the second root table. If we have to calculate the second element of the third row, which is 4, its value should be equal to 5 into 4 minus 2 multiplied by 0 divided by 5. 2 into 0 will give 0. After that, we can cancel 5, which will give 4, which is exactly the same value of the last element of the first row. I hope you are getting what I am trying to say. This point you are supposed to find yourself by doing a lot of practice of different questions. Now, we will discuss more theoretical points about this topic. First of all, it might be possible there is no need of forming the root table to determine whether the system is stable or not. There are 2 necessary requirements which must be followed by the characteristic equation, then only you should move forward for finding the Routh array. These 2 conditions are there should not be any term missing in the characteristic equation, and the second condition is all the coefficient of the characteristic equation must be positive. Now the next question is, what if the transfer function does not satisfy any of these 2 conditions? In that case, you can simply say that the system is unstable. There is no need to form the Routh array. Let us consider a few examples. Like, suppose the characteristic equation of a system is 4s4 plus 5s raised to the power 3 plus 7s plus 8. In this expression, there is no term considering s raised to the power 2. We can also say that the coefficient of s square is equal to 0. So, without forming the Routh array, we can simply say that the system is unstable. Let us take another example. Here, in this characteristic equation, the third term is negative, which is minus 6x square. Negative coefficients are also not possible. Therefore, this is also unstable. Sometimes you have to use a little bit common sense also. For example, suppose there is a characteristic equation in which all the coefficients are negative. Then there is a possibility that the system might be stable. In such cases, it will be much better if you take the negative sign common and shift that negative sign into the numerator. By doing so, you will get all the positive coefficients in the characteristic equation, which is the denominator of the transfer function, and the negative sign will shift to the numerator of the transfer function. But even after that, there is no guarantee the system is stable. You have to form the Routh table to determine whether the system is actually stable or not. If the characteristic equation follow any of these 2 conditions, then the system will be definitely unstable. However, If a characteristic equation follow both these conditions, it does not mean the system is stable. It simply means you should go forward to form the Routh array and determine system stability from Routh stability criteria. There is also a possibility that there is an unstable system which you can see clearly, but still, in the question, you are not to determine whether the system is stable or not. You are supposed to find the number of roots in the right half of S-plane. In that condition, you have to form the Routh array even if the necessary requirements are not being followed. This happens because to determine the number of root in the right half of S-plane, you have to calculate the number of sign changes, which obviously you can find only through Routh array. Whatever we have discussed so far is actually quite simple cases, but sometimes you may face few special cases in which you have to follow certain other steps to form the Routh table. These cases are special cases. The first special case is when the first element of any one row of Routh array is 0, but the other elements are non-zero. In this case, we have to replace the 0 with epsilon, where epsilon is a very small positive number mostly, but sometimes we have to assume epsilon to be negative value. Many students think that epsilon is always positive. However, that is not true. First, we will clear when and where we have to put the value of epsilon positive and where we have to put negative value. After that, we will see how to proceed to form the Routh table after replacing the value of 0 with epsilon. Suppose this is the Routh table. Here, the first element of the second row, which is 1, is actually positive, and that is the main reason why we have to assume the value of epsilon to be a positive value only. In other words, the positive or negative sign of epsilon is actually dependent upon the value of the element just above the value of epsilon. And the main logic behind this is very simple, which is we don't introduce sign change by ourselves. As you might have observed by now that the sign change in the Routh table plays a very important role, and if we ourselves produce a sign change, then it don't make any sense to form the Routh table at all. So we by ourselves never try to introduce a sign change. If the value just before the epsilon is positive, then we have to assume the epsilon value to be a very small positive value, and if the value is negative, then the epsilon value should also be negative. After that, the procedure is actually exactly the same as a normal case. Now we are having the complete Routh table, which is having few elements in terms of epsilon. Our next step here will be to find the limiting values of all the elements in the first row which has epsilon in them. We are actually more interested in the sign of the value rather than the exact value. The element in the third row is positive, as we have already assumed the value of epsilon to be a positive quantity. In the fourth row, however, you have to be little bit careful. 2 minus 3 upon epsilon, where epsilon is a very small value tending towards 0 and is positive. After calculating, you can simply say this expression will give a negative value. There is no need to calculate the exact value. You can simply put negative in the Routh table. Now, in this special case, there are two possibilities. The first possibility is if the sign of the coefficient above the 0 element is same as that of the element below it, then it indicates that there is a pair of imaginary roots. However, this is definitely not the case here. The second possibility is if the sign of the coefficient above the 0 element is opposite of the element below it, then the system is unstable. Number of sign changes represent the number of poles in right half S-plane. In our example, there are 2 sign changes, so there will be 2 roots which will lie on the right half of the S-plane, and as such, the system will be unstable. Now let us see the second special case. The second special case is when all the elements in any one row of the Routh array are 0. This condition indicates there are symmetrically located roots in the S-plane. The polynomial whose coefficients are the elements of the row just above the row of 0 is particularly defined as the auxiliary polynomial. It actually plays a very important role in completely solving the Routh array in this special case. There are few steps what one should follow to proceed to solve such type of cases. First, you have to form the auxiliary equation by using the coefficients of the row just preceding the row of zeros. After that, take the derivative of the auxiliary equation with respect to the Laplace variable s. Now, you have to replace the row of zeros with the coefficients of the derivative of auxiliary equation. After that, you have to proceed same as that of a normal case. There is no way each and everything whatever I just said is clear to you. So, let us take an example and solve it and see how to proceed in such cases. I have taken a random Routh table in which first two rows are identical. The next row will come 0, 0. Now, our first step will be to form the auxiliary equation, and after that, we will differentiate the auxiliary equation. The next step will be to replace the row of zeros with the coefficients of the derivative of the auxiliary equation. The coefficients came 4 and 12, which is having a common factor of 4. So, for easier calculations, it will be much better if we divide the whole row with 4. The Routh table up to the third row will look like this. Afterwards, we have to simply solve this Routh table as we do for a normal case. In this case, we have seen there is no sign change, but this special case is actually little bit lengthy. You still cannot say that the system is stable. For that, there are two more special characteristics of auxiliary equation which you should always remember. The first is the auxiliary equation is always an even polynomial. That is, only even powers of s appears. The second point is actually more important, which is the roots of the auxiliary equation are also the roots of the original characteristic equation. The second point will be used approximately every time you have to deal with this special case. We already have the auxiliary equation. We have to simply find the roots of this equation, which will come out to be equal to plus minus 2j and plus minus under root 2j. So, we are having 4 purely imaginary roots, which ultimately makes the system marginally stable. I hope you have understood all these points until now. These special cases may be a little bit lengthy, but still these are not difficult at all. Now let's see some limitations of Routh-Hurwitz criteria. It is only valid for LTI systems. The characteristic equation of the polynomial should have positive and real coefficient. It is not applicable for an infinite series such as polynomial containing sine, cosine and exponential term. The sign changes in the first column determines the roots lying in the first half S-plane, but they don't determine their values. When the system is marginally stable with oscillatory response, to find the frequency of oscillations, the auxiliary equation should be an even polynomial of order 2. Frequency of oscillation is nothing but the root of the auxiliary equation. There is one more topic which is completely for numerical problems. For the stability of the system, we just try to find whether there are any root which lie on the right hand side of the S-plane or not. But sometimes questions may also come where you have to shift the origin and tell whether the system is stable or not. In such cases, the most important equation you have to remember is S equal to S1, which is the Laplace variable S after the moment of origin, minus sigma, where sigma is the distance between the two origins. This is actually a very simple equation, but still many students commit silly mistakes. Keep in mind, I have shifted the S-plane in the negative direction, but if you have to shift the origin towards the right side, then you have to put the value of sigma to be negative. There can be some good questions which can be asked from this topic. Like for example, consider these two questions. Determine whether the provided system is stable or not. And the second question is determine whether the provided system is having all the poles on the left hand side of S-plane or not. These two questions are actually exactly the same. In both the equations, you have to simply form the Routh array and determine whether the system is stable or not. But suppose there is a question where you have to determine whether the system is having all its pole lying left 2 minus 4 on the real axis or not. In this case, first you have to shift the origin from 0 to minus 4, and after that only you can apply the Routh-Hurwitz criteria. In this case, first you have to put the value of sigma equal to 4, then take the characteristic equation, put the value of S equal to S1 minus 4, reform the characteristic equation, and then only form the Routh array to find whether the system is stable or not. The second type of question which can be asked from this topic is that determine whether the following systems have all their poles on the left hand side of the line whose equation is s is equal to -9. You will be provided two systems, and the third part of the question is which system is relatively more stable. Now simply assume the system 1 is having all the poles on the left hand side of the line whose equation is s is equal to -9, whereas this is not the case for the system 2. But we have already discussed in earlier chapters that the system which is having its most dominant pole most distant from the origin is actually the most stable. So in this case, if the system 1 is having all its pole lying on the left hand side of the line whose equation is s equal to -9, then definitely it is more stable. To solve the first two parts of this question, you have to first shift the origin and then form the Routh array, whereas for the third part, you only need theoretical knowledge. If you are expecting from me that I will be teaching all the relevant topics for undergraduate level studies, then it is fine, but if you are expecting from me that I can tell you all variety of questions which can be asked, then obviously it is not possible. All the important points are discussed, now you have to only do the practice. You should give a look to the short notes which I have attached in the video's description. I hope you have enjoyed this lecture.